Next, we will consider another problem. It is consider a flow at speed 50 meter per second flowing over an elliptical strut at an angle of attack 0. You have to find the velocity just outside the boundary layer, okay, which in inviscid flow is happens to be on the surface of the ellipse at the point of maximum thickness. The ellipse has a fineness ratio of 4. Elliptical strut, that is a column whose cross section is ellipse, that is what is an elliptical strut is, of fineness ratio 4. The free stream speed is 50 meter per second, angle of attack is 0 degree. Find the velocity at the point of maximum thickness. So, we have elliptical strut find velocity and pressure at this point. So, first we have to find the transformed circle, okay? The transformed circle. In this case, we know that the center of the circle will coincide with the origin in the xy eta plane. Okay? The center of the circle will coincide with the origin in the xy eta plane. and its radius will be related to the fineness ratio or in terms of ellipse with the major and minor axis. Now, at the point of maximum thickness, what we have? And this is related to, if you look to the transformed circle, this is related to or we can write, if you remember that this was the semi minor axis and we will be interested in terms of theta, which is pi by 2. So, now how will we find r? Yesterday in that problem also we had something like this. Here also, since C is not specified, the length of the ellipse is not specified, we cannot explicitly find how much is B, but we will be able to find the ratio. This is this. What is the fineness ratio? Fineness ratio is 4, but the fineness ratio is also given by C by T, okay, but in terms of that radius r and B, r square plus B square by r square minus B square. So, we have r square plus B square by which, if you want, you can also write as r by B plus B by R Now, find how much is r by b. Do not try to find r or b separately, because we are not we do not need even r and b separately. How much? R by b equal to okay, or r square by b square equal to five by 3. Now, we have to find the velocity at the point of maximum thickness. So, first you have to find how much is the velocity there on the circle. How much is the velocity on the circle at that point, at theta equal to pi by 2, how much is the theta equal to pi by 2. So, this will make it simply 2 q infinity. That is 100 meter per second. This also comes directly from the velocity formula for the circle that we did earlier. So, if you remember, you can directly use it instead of writing this expression, you can directly write as the velocity at that point is. Now, what is the velocity on the ellipse? This divided by dz d zeta at theta equal to pi by 2. So, what we need to find dz d zeta at theta equal to pi by 2. How much is zeta at theta equal to pi by 2? Coordinate of that point. Yes, you are telling it correctly. Do not use t. T is for ellipse. The circle do not have t. Zeta is for the circle. Pi by 3. Pi by 3. We have already used theta equal to pi by 2 and now you are saying it is pi by 3. Which point is that? See, this is the transformation. Let us have it once again. Okay. So, this is the point where we are interested to find the velocity. To which point this has transformed? Theta equal to pi by 2, this point. What is this point? I r. What pi by 3? Okay, so, it is I r. So, this becomes at theta equal to pi by 2 is what happened. Zeta is I r, not simply r, I r. So, that I square become minus 1. So, it has become plus. So, this becomes 1 plus 3 by 5, that is 8 by 5 equal to 1.6. So, you see that we do not need either B or R, what we need is B by R. Okay. So, now we can find the velocity . This I think will come as something 62.5. Okay, fine. Another pressure. How to find the pressure? C p equal to 1 minus q square by q infinity square, this let us call it q. So, that is all. Okay. How much is this?
minus 0.56.
That is all. Or if you want to express pressure in terms of your conventional that Newton per meter square unit, then you have to multiply this by half rho q infinity square. But often you will be asked to find the pressure or lift, usually that will mean pressure coefficient and lift coefficient. Let us try one more before we conclude this. topic. This will be a good example. A 20% thick Joukowsky airfoil set at 0 incidence to a free stream of 10 meter per second. A 20% thick Joukowsky airfoil set at 0 incidence to a free stream of 10 meter per second has a lift coefficient of 0.3. Find the lift coefficient at 5° incidence. Find the lift coefficient at 5° incidence and the velocity at the nose of the airfoil. And the velocity at the nose of the airfoil. What will you do? It gives lift coefficient at 0° angle of attack is 0.3. You have to find the lift coefficient at 5°. What is the formula for the lift coefficient? If you remember, it is CL equal to 2 pi into 1 plus epsilon sin alpha plus beta. Okay. When alpha is 0°, your lift coefficient is 0.3. So, we have let us say q infinity equal to 10 meter per second, T by C max equal to 20%, alpha equal to 0° corresponds to CL equal to 0.3. You have to find when alpha equal to 5°, how much is CL. Now, lift coefficient is given as 2 pi into 1 plus epsilon sin alpha plus beta. Epsilon is related to that T by C max. So, T by C max 20%, that leads 1.299 epsilon equal to 0.2 or epsilon equal to 0.154. So, we have 2 pi into 1.154 into sin beta equal to 0.3. So, that will give you beta. It will give beta equal to 2.37 degree. So, now you can find what the CL when alpha is 5. Next, you have to find the velocity at the nose of the airfoil. So, once again same procedure, you have to find what is the velocity on the corresponding circle at that point and divided by dz zeta at that point. So, what is the point at nose? At airfoil nose, how much is theta? At airfoil nose, how much is theta? Pi. Okay. Now, what is the circle now in this case? You have to find out dz d zeta at theta equal to pi. Points on circle, points on transformed circles are given as zeta equal to zeta naught plus r e to the power I theta. Okay. What is zeta naught? Zeta naught is minus b epsilon plus r sin beta, I r sin beta. Zeta naught is minus b epsilon plus I r sin beta plus r e to the power I theta. So, the point that corresponds to airfoil nose epsilon is known, beta is known, theta is pi. So, substitute those values. Theta is pi. E to the power I pi, how much is that? minus minus 1. So, okay. So, it becomes minus r or also you can express in terms of b. See, there are two r and b. We have a relationship between r and b. R is how much? B into 1 plus epsilon. So, we will have only b. That of course, we cannot find, it will remain as b. Okay. And you please check the calculation. What I have got is something like this, minus 1.308 b plus 0.0477 b I. This data, just to denote that this is this corresponding to the nose point, we will just give a subscript n, that this is the point corresponding to the nose of the airfoil. This is the point on the circle that corresponds to the nose of the airfoil. Now, we can find what is dz d zeta. Dz d zeta corresponding to that nose is 1 minus okay. This has come to be I have left it like this 1.2264. Please check these calculations. Now, the velocity on the airfoil, free stream is 10, q infinity is 10, alpha 5, beta 2.37, theta pi. Okay. So, if you substitute that, this has come to be minus 4.3086 I.
So the q infinity value that we use here as 10 meters per second is given in the z plane. So should it be transformed before using it?
No, the free stream, that q infinity will not change, free stream speed will not change, the free stream speed will not change,
In both z and zeta.
that will not change. We have never changed that. The streamlines will change, but the magnitude of the velocity stream, that will not change. This has come to be I think I earlier told you how the pressure is measured, pressure acting on a body, how it is measured. You have not done any experiment as yet. See, on the surface of a body, a very small hole is drilled, okay, and then some probe, usually it is just a tube, is inserted through the body, so that it is flush to that surface. It is not protruded from the surface, it is just flush to the surface, and through the hole that it is connected. Okay. And then of course, that tube is connected to another measuring device, whatever it can be. It can be a simple manometer or it can be a pressure transducer or anything. So, that hole serves the purpose of a sensor, it senses the pressure. And if the flow is tangential to the hole, then that hole will simply sense the pressure, the static pressure. Of course, however, if the hole is normal to the flow, then it will sense the total pressure, the stagnation pressure, which is P plus half rho u square for incompressible flow. So, our next problem deals something with like this. A long elliptic cylinder of thickness to chord ratio of 1/7, a long elliptic cylinder of thickness to chord ratio of 1/7 is set at an incidence of 0 degree, in an air stream of 35.4 meter per second. Calculate the pressure difference or calculate the difference between the pressure, pressure holes set in the nose and at the point of maximum thickness. We have pressure hole here at the nose and at the point of maximum thickness. You have to find the difference between pressure holes pressure at these 2 points. As before, the way we have done earlier, this fineness ratio of 7 implies that b square by r square equal to 3/4. We have done it already, exactly same, this will give b square by r square equal to 3 by 4. Now, let us see what we have to find first before trying to do it. Let us designate these 2 points as 1 and 2, 1 and 2. We want what we want? Difference between pressure at 1 and 2, P 1 minus P 2. Now, let us, this is an inviscid irrotational flow, ideal flow. So, the Bernoulli's equation applies everywhere. Bernoulli's equation applies everywhere in the simplest form, or what we have is P 1 plus half rho, if the velocity here is q 1 and here it is P 2 plus half rho. So, what we want in essence is P 1 minus P 2 equal to now q 1 is 0, q 1 is 0, that is the stagnation point. Of course, you can put it in the formula and check. We can also check it. Let us see that this is a stagnation point. We can also check velocity at the nose, now nose corresponds to theta equal to pi. So, the velocity on the corresponding point on the circle alpha is 0, beta is 0, alpha is 0, beta is 0, theta is pi. How much is this? 0. So, this divided by dz d zeta is again 0. So, this is confirmed. Now, what is the velocity at the point of maximum thickness? See, this time we will not repeat it again, already we have done. So, we will just use the final result. If you remember how much it was, 2 into 35.4 divided by 1 plus 3 by 4, or that is 1.75. We will take it from there. And that comes to be 40.46. And now we can complete that P 1 minus P 2. Of course, we do not know what is the rho. Okay. Let us assume that this fluid is air and take the standard value of air density, which happens to be 1.225 kg per meter cube. Okay. If no density is specified, but it is air, then you can always use the density to be 1.225 kg per meter cube. Otherwise, of course, you can leave it in the term of rho, it does not matter. But using that 1.225, this happens to be something 1 kilopascal practically. Approximately 1 kilopascal. So, as the fluid has travelled or the air has travelled from the nose to the point of maximum thickness, it has experienced a suction of 1 kilopascal. Consequently, it has accelerated from 0 to about, in case of a circle of course, it is twice, but here it is how much, from 0 to 46, 0 to 40. At the nose the fluid velocity has become 0, from there it has accelerated to 40 with a simultaneous pressure drop of nearly 1 kilopascal. So, with this we will conclude our discussion on this conformal transformation or the transformation technique, but two things I will just ask you to do. If you can't, we can discuss it later. That is, I will ask you to find the moment coefficient, the lift coefficient we have found for Joukowsky airfoil. I will ask you to find the pitching moment coefficient, okay, and the aerodynamic center. If you remember aerodynamic center, I think we have defined earlier. Aerodynamic center is the point about which the pitching moment is independent of lift coefficient or angle of attack. There is a point about which the moment will not change as the angle of attack changes. For any other point, the pitching moment will be different at different angle of attack, but when you take moment about the aerodynamic center, the moment will not change with the angle of attack. So, this I will ask you to do. about aerodynamic center. And the location of the aerodynamic center sorry, not y, this is z.